What's up, Atlas? It's your dad, Professor Panda. Today we're going to be looking at essential topic number 5, analysis of trusses and frames, and obviously we're going to be answering the questions, what problems do I need to know how to solve in order to pass this quiz? But beginning a lot of questions about this particular problem, but before we jump right into it, we're going to review what the things that we need to know before we can pass this quiz. Identifying 0 force and 2 force members, not going to be critical for today's exercise. When to use method of sections versus joints. This isn't a real world problem. The problem statement tells us what method they would like us to use, so irrelevant, but we're going to be identifying some things today. Next week we're going to be identifying multi-force members and how to break the frame or machine into multiple free body diagrams. But for today, we're going to be going down the path of a method of sections. And this problem statement just says, determine the force in members D, F, E, F, and E, G of the truss shown. So let's go top down. I've already got my truss structure here laid out. And step number 1, obviously you've known this before, we're going to do a free body diagram. Okay, free body diagram of what is the question? So students are generally going to want to solve for the reaction forces first. So let's go down that rabbit hole and see if it's fruitful. So quickly sketch out my free body diagram. This goes here. And 1, 2, 3. 1, 2, 3. Not super exact, but we don't need to be, because really what we're interested in here is the reactionary forces from the pin and roller at alpha and I don't know what N is. We're going to call him Nemo today. Okay, so here's the 16 kilonewton forces. And N has a roller, so we're going to be giving that a NY force. And A has a pin, so it's going to get 2 forces. AY and AX. Okay, so I'm going to leave the distances off here for just a moment, and we'll get into solving for the reactionary forces. If you've ever met Christopher will definitely make us do some of the force in the X direction first. So let's start there. So some of the force in the X are going to be AX plus 16 kilonewtons minus 16 kilonewtons. Set that equal to 0. 16 and 16 go to 0. So AX equal to 0. What a surprise. Okay, next one is going to require a little bit of thinking on our behalf. So let's do some of the forces in the Y direction. And we're going to have AY plus NY equal to 0. Okay. Interesting. We haven't had a problem like this before. And it's been tripping up a couple of my students. So there's a couple things that be going on here. All right, let's just solve for AY. Okay, so we can have this relationship. And there's two possible outcomes that we could have with this relationship. One of the outcomes could be that N sub Y is drawn backward. Okay, but we know this is not the case. So if NY is backwards, then, or if NY is not drawn backwards, then we have the second case where NY is equal to 0. Much more likely the case, because the problem didn't give us any weight of the structure. And so it would seem that neither reaction forces is providing upward lift of this structure. If we were given weight, then we could solve for AY and NY. Alas, we don't, so we're going to go with the second option of NY equal to 0. And so AY is going to equal to 0. And now we can move on to solving this problem. Okay, so now that we got the reactionary forces out of the way, now let's deal with what the problem is asking us for. Okay, so returning to the question, RTQ, we want Delta Foxtrot, which is this guy. We want Echo Foxtrot, which is this guy. And we want Echo Golf, which is this guy. Oh, that's wrong. It's this guy. We will fix that up with my whiteout and redraw that line back in. Delta Foxtrot, Echo Foxtrot, Echo Golf. Okay, those are the three sections, or those are the three members that we were in question. So it seems obvious that we're going to make a cut here. And I'm going to call this section AA, which means for step number 2, we are going to be doing a free body diagram of let's go at A-A. And with sections, obviously we get a choice of right or left-hand side. I'm going to choose the left-hand side, it's less to draw. So of left side. Alrighty, so let's draw yet another free body diagram. And we're going to end with only points delta and echo. So here we have A, B, D. Something like that. And I'm going to go ahead and label these to make sure we have everything. C, D, and E. Okay. Let's do the externally applied forces, which is going to be acting at A still of 16 kilonewtons. Okay, and we cut between delta and foxtrot, so I'm going to always assume that the members that I cut are going to be in tension. So I'll start at D and go upward and call that tension delta foxtrot. Okay, at echo, it's going to be going vertical. I'm going to call that one tension echo foxtrot. And off of here will be another diagonal force at tension echo golf. Terribly small drawing here, but you get the idea about where I'm going with this. Okay, now some dimensions to make our free body diagram complete. So it looks like typically the vertical spacing is going to be 4 meters apart. So 4 and 4 meters. Draw those in. Horizontally, everything is 3 meters. So we're going to do 1, 2, 3 of those. Okay, complete free body diagram now. Okay, so now that we have our free body diagram of section AA on the left hand side, now it comes time to be a little bit clever about what points we choose to take moments about, or if we take in Newton's second law, some of the forces in X or Y. If I do some of the forces in X or Y, it doesn't seem very fruitful to me because I'm going to have 3 forces in the vertical direction, not helpful since I'm only going to have 2 equations. So I'll skip over some of the forces in X and Y immediately, and I'm going to go on to pick a point, probably echo, because if I pick point echo, tension EF and tension EG do not participate in the moment calculation. They don't participate because they have a 0 moment arm. So let's pick some of the moments about point echo. Okay, I pick that point, the 16 kilonewton force will participate. So let's open parentheses, and it's going to participate at a distance of 3 and 3, 6 meters. Multiply that by 16 kilonewtons. Close parentheses, and you know, every time I close parentheses in a moment calculation, it triggers me to draw this little diagram here. My positive convention here, so that's positive x, positive y, and positive moments. Okay, this little diagram shows me that I'm using a regular Cartesian right-handed coordinate system. So this one we can either use this is actually the cross product, right? R cross F. Let's do this. Summation of R cross F. And if we want to stick to IJK hats, we can, or we can use a little cheater method. So I'll just carry out the multiplication, but I will insert a positive or negative based on the R cross F schematic. Okay, so the first time I'm using this guy. This is my little R cross F. Okay, so this is going to be my pin at echo. So if I put a pin at echo, and this is my force, my 16 kilonewton force, it's going to be rotating this direction, which agrees with my positive convention, which means this remains positive. Okay. We'll add to this another quantity. The only other one that is going to participate is tension delta foxtrot, but only one component of delta foxtrot is going to participate. Okay, so it is going to be participating at a distance of 4 meters, and we're going to multiply that by TDF, but not the entire strength of TDF. Okay, we need to back up and draw a triangle here where we have this triangle. We're going to call that alpha. So this will be alpha. This will be 3 foot. This will be 3 meters. That'll be 4 meters. So to solve for that, we say that alpha is equal to tan inverse of 3 over 4. So tan inverse of 3 divided by 4, 36.86 degrees. Okay. So we will keep this as the sine of alpha. Remember, I use capital S for sine, lowercase, or the sub alpha of this. So this big S just means sine. You see a big C means cosine. Okay, and we close that off. And if I put a pin at echo, and I line up where TDF is going to be pointing, goes in this direction, and so I get a negative moment. So I'm going to sneak a negative in there. Super difficult to see. I should have left some room, but this term will be negative. This one will be positive. Okay, since I'm taking the moments about echo, TEF and TEG don't participate, and so that finishes off this equation. So since TDF is the only unknown variable, we can solve for that directly. So it's negative, and I want to make it positive, so I'm going to move this whole term to the right-hand side and then swap. Okay, so TDF equals, it's attached with 4 meters and a sine of alpha. So when I go to the right-hand side, I'm going to divide that off. So I can divide that off here, 4 meters sine of alpha. Since this term went to the right-hand side, this term didn't move, so it remains the same. It's positive still. So 6 meters times 16 kilonewtons. Okay, let me populate some values in here. So 6 meters times 16 kilonewtons over 4 meters sine 36.86. Oh no. I have to change batteries. I'll be right back. Okay, we're back. So we have 6 times 16, close parentheses, divide that, open parentheses, 4 times sine. And it would be really tempting to use this 36.86, but with you having your calculator, just go up and grab that value. 40. So TDF is going to equal 40 kilonewtons. Okay, and if we do the unit analysis, meters and meters will cancel. Kilonewtons is left, so we're right on track there. And so we want this value, so I'm going to go ahead and put my want table up here. And so we want member DF, and that's going to be something kilonewtons, and it's going to be in either tension or compression. And since we just solved for TDF, we're going to report 40 kilonewtons, and we guessed that our TDF was going to be in tension. It came out positive, so we know that it should be in tension. Okay, while I'm here, I'm going to go ahead and put in Echo Foxtrot, something in kilonewtons, tension or compression, and Echo Golf equals something kilonewtons, tension or compression. Okay, box this answer, and now I can move on. What to do next? So, since I have this guy already in TDF, I need to solve for one other variable. So I can either choose to do a moment about another point, or I can rely on some of the force in the X and some of the force in the Y. I know what I would prefer. I would prefer to do more moment calculations, but my students are a little bit timid about doing moment calculations. They're much more comfortable using some of the force in the X and Y. So we can use some of the force in the X direction on section AA to get TEG directly. Since TEF does not participate in a horizontal forces calculation, we should be able to pop out TEG directly. Let's do that. 3, I'm gonna do some of the forces in the X direction equal to 0. And so we'll start out here with 16 kilonewtons. We will add to that tension delta foxtrot, not the entire thing. We only want the cosine of alpha of tension delta foxtrot. Okay, tension echo foxtrot does not participate. It's horizontal force. So tension echo golf does participate, but only part of it. And that is going to the same triangle that we built here. Since the bottom rails and the top rails are perpendicular, or are parallel, so they should have the same alpha here, same angle. So we'll put another cosine of alpha there. Set that equal to 0. And since we know DF, we're looking for EG. So I'm going to take TEG and write it out first. It's attached with the cosine of alpha, so let's divide that off. Now the 16 kilonewtons and the tension of delta foxtrot, that's all positive, but it has to move to the right hand side to isolate TEG. These are both going to be negative. Minus TDF cosine of alpha. Okay, let's put some numbers into these variables. It'll be negative 16 kilonewtons minus 40 kilonewtons cosine of 36.86. Divide that by cosine of 36.86. All right, let's plug and chug. Negative 16 minus 40 cosine, and again, we're going to grab this number. Okay, that's the numerator, and we will divide all of that by the cosine of this number. Negative 60. So TEG equal negative 60 kilonewtons. Okay, we got a negative number. What does that mean? All that means is that TEG, this variable here, we guessed the wrong direction. I always guess in tension. It came out negative. So TEG, when we report, will be 60 kilonewtons in compression. So that's all that means right there. And again, we will box this answer. And now we can move on to step number 4. So since we have that one taken care of, the low-hanging fruit, sum of the force in the y direction, and that will complete this problem. So let's do some of the force in the y direction are going to equal TDF, not the entire strength. It's going to be the sine of alpha plus TEF, full strength since it's vertical. And we're going to add to that TEG sine of alpha, set that equal to 0. No other forces participate, and we're only looking for EF. The other two are going to go to the right-hand side. We're going to have TEF equal to negative TDF sine of alpha minus TEG sine of alpha. Okay, and remember, these positive and negatives have come from Newton's second law. Okay, so now I'm going to substitute values in here. Let's do it right underneath so it's very clear what happens here. So negative, what is TDF's value? 40 newtons, 40 kilonewtons. Sine of 36.86 minus, what's TEG's value? That's negative 60 kilonewtons. Sine 36.86. Okay, so this negative 60 came from the value that is held within the variable TEG, and this negative sign came from some of the force in the y direction. Okay, very important, very easy to mess that up. Okay, so let's carry out this calculation and see if we can't solve what TEF is equal to. So we have negative 40 sine. Go ahead and grab that number again. Let's go ahead and enter that one. So negative 24, this will be plus 60 sine. Grab that 36 value again. 12. Box that. Let's go ahead and report that as EF being 12 kilonewtons. It's positive, so it remains in tension. And there we have it. Homework help. Quiz 5, example 2, utilizing method of sections to find a couple of members within the truss structure. Hope you found this valuable. If you made it to this far to the end of the video, do all the things, like it, subscribe, comment on it, ask any questions. And as always, happy math. Bye-bye.